What if everything you've ever been told about the beginning of the universe is wrong? What if the Big Bang wasn't actually the beginning at all? In February 2023, the James Webb Space Telescope captured images of galaxies that, according to our current understanding of physics, shouldn't exist. These aren't just old galaxies. These are massive, fully formed spiral galaxies that appear to have existed just 200 to 300 million years after the supposed Big Bang. But here's the problem that's keeping cosmologists awake at night. These galaxies are so large, so mature, and so perfectly structured that they would have needed billions of years to form. Not hundreds of millions, billions, which means they would have had to start forming before the Big Bang itself. We're not talking about a small error in our calculations. We're talking about observations that fundamentally break our entire model of cosmic history. The universe, according to these images, is impossible. Let me be crystal clear about what we're looking at here. The James Webb Space Telescope has observed galaxies designated as JADES GZZ13-0, JADES GZZ12-0, and JADES GZZ110. These galaxies have redshift values that place them at cosmic distances corresponding to when the universe was, supposedly between 200 and 350 million years old. But these aren't primitive blobs of gas. These are sophisticated spiral galaxies with distinct structure, massive stellar populations, and characteristics that suggest they'd been evolving for 2 to 3 billion years. That's 6 to 10 times longer than the entire age of the universe at that point. It's like finding a 60-year-old man's birth certificate that says he was born 8 years ago. The math doesn't just fail to add up. It collapses into absurdity. Before we go any further, I need you to do something. Hit that like button right now, and smash that subscribe button, because what you're about to hear over the next few hours is going to fundamentally change how you understand reality itself. Drop a comment below telling me what country you're watching from and what time it is where you are right now. I want to see how this revelation is spreading across the planet in real time. Are you watching this at midnight, unable to sleep because your mind is racing? Are you listening during your morning commute, about to have your entire day recontextualized? Let me know, because we're all in this together, standing at the edge of a cosmic mystery that threatens to unravel everything we thought we knew. Now, let's start from the beginning, but not the beginning you think. To understand why these James Webb discoveries are so catastrophic to modern cosmology, you first need to understand what the Big Bang theory actually says. And I can almost guarantee you that what you think you know about the Big Bang is wrong. Most people imagine the Big Bang as an explosion, like a bomb going off in space with matter flying outward into an empty void. That's not what happened. The Big Bang wasn't an explosion in space. It was an expansion of space itself. There was nowhere for it to happen because space itself didn't exist before it. There was no when it happened in because time itself began at that moment. The Big Bang is the moment when space-time itself came into existence. According to the standard lambda-c/dm model of cosmology, our current best theory of the universe's history, the Big Bang occurred 13.8 billion years ago. In the first fractions of a second, the universe underwent a period of exponential expansion called cosmic inflation, growing from smaller than a subatomic particle to the size of a grapefruit in less time than it takes light to cross a proton. The universe was filled with an incredibly hot, dense plasma of fundamental particles. As it expanded and cooled, these particles began to combine. After about 3 minutes, protons and neutrons formed the first atomic nuclei, mostly hydrogen and helium. But the universe was still too hot for complete atoms to form. It remained in opaque plasma for about 380,000 years, until it cooled enough for electrons to combine with nuclei and form neutral atoms. This moment is called recombination, and it's when the universe became transparent for the first time. The light from this moment is what we observe today as the cosmic microwave background radiation, a faint afterglow of the Big Bang that fills all of space. After recombination came what cosmologists call the Dark Ages, a period when the universe was filled with neutral hydrogen gas, but no stars had yet formed. This darkness lasted for about 100 to 200 million years. Then, slowly, the first stars began to ignite, formed from slight density fluctuations in the primordial gas. These weren't stars like our Sun. They were massive, short-lived monsters called population 3 stars, made entirely of hydrogen and helium, because no heavier elements existed yet. These first stars lived fast and died young, exploding as supernova and seeding the universe with the first heavy elements. Over hundreds of millions of years, these stars began to cluster together under gravity, forming the first proto-galaxies. These early galaxies were supposed to be small, irregular, chaotic collections of stars. Not the majestic spiral galaxies we see today, but messy, primitive structures. According to our models, it should have taken billions of years for galaxies to grow large and organize into the beautiful spiral and elliptical forms we observe in the nearby universe. This timeline isn't just speculation. It's based on decades of observations, mathematical models, and physics we've tested in laboratories here on Earth. The cosmic microwave background has been mapped in exquisite detail by satellites like COBE, WMAP, and Planck. The pattern of temperature fluctuations in this radiation matches our theoretical predictions with stunning precision. We've observed the ratio of hydrogen to helium in the universe and found it matches what nuclear physics predicts should have been forged in the first few minutes after the Big Bang. We've watched the expansion of the universe by measuring the redshift of distant galaxies and found that it's accelerating, driven by dark energy. Every observation has fit together into a coherent picture, until James Webb looked deeper than we'd ever looked before. Think of it like this. Imagine you're an archaeologist and you've developed a detailed timeline of human civilization based on countless excavations. You know that writing was invented about 5,000 years ago. You've found the evidence. You've carbon dated it. Everything checks out. Then one day, you dig in a layer of earth that you know is 7,000 years old, and you find a perfectly preserved copy of a Shakespeare play. Not something similar to Shakespeare. Actual Shakespeare, with the same language, the same sophistication, the same mastery of literary technique. You would have 3 options. Your dating method is wrong. Someone buried a modern text in ancient soil. Or Shakespeare existed thousands of years before writing was supposed to have been invented. Each option breaks something fundamental about what you thought you knew. That's where cosmology is right now. The James Webb Space Telescope launched on December 25, 2021, and began science operations in July 2022. It's the most powerful space telescope ever built, with a mirror 6.5 meters in diameter, compared to Hubble's 2.4 meters. But size isn't the only advantage. Webb observes in infrared wavelengths, which allows it to see things Hubble couldn't. When light travels across vast cosmic distances, the expansion of space stretches the wavelengths, shifting visible light into the infrared. This is called cosmological redshift. The more distant an object is, the more its light is redshifted. By observing in infrared, Webb can see galaxies so distant that their light has been traveling toward us for over 13 billion years. We're literally looking back in time to when the universe was in its infancy. Within the first few months of observations, Webb began detecting galaxies at redshifts higher than anything Hubble had ever seen. Redshift is measured using the variable z. A redshift of z equals 1 means the universe was half its current size when the light was emitted. A redshift of z equals 10 means the universe was 1/11th its current size. Hubble's deepest observations had found a few galaxies at redshifts around z equals 9 to 10, corresponding to about 500 million years after the Big Bang. These were faint, small, and exactly what theory predicted. But Webb started finding bright, massive galaxies at redshifts of Z equals 12, 13, even candidates at Z equals 16 and higher. At Z equals 13, we're looking at light that left those galaxies just 325 million years after the Big Bang. At Z equals 16, we're looking back to roughly 250 million years after the Big Bang. Here's what will blow your mind. In August 2023, a team led by Ivo Laub at the Swinburne University of Technology published a paper analyzing Webb's observations of 6 massive galaxies at redshifts between Z equals 7.4 and Z equals 9.1. These galaxies existed between 500 and 700 million years after the Big Bang. Using spectroscopic measurements, they determined that these galaxies had stellar masses between 10 billion and 100 billion times the mass of our Sun. Our own Milky Way galaxy has about 100 billion solar masses and stars, and it's taken 13 billion years to build up that mass. These galaxies had comparable masses when the universe was just a tiny fraction of its current age. Laub's team calculated that for these galaxies to have formed so many stars so quickly, nearly 100% of all the available matter in their region of space would have had to convert into stars. Not just the gas, but virtually every atom would need to become part of a star. That's absurdly efficient. In the real universe, star formation is messy and inefficient. Most gas never becomes stars. It's blown away by stellar winds, heated by radiation, or just never collapses densely enough to ignite fusion. The absolute maximum efficiency we've ever observed in the nearby universe is about 10 to 30%. These early galaxies would need to be 3 to 10 times more efficient than anything we've ever seen. But it gets worse. It's not just that these galaxies have too much mass. It's what kind of mass they have. Spectroscopic observations show that these galaxies contain old stars. Not young, bright, blue stars that just formed, but older, redder stars that have already gone through significant evolution. When a star forms, it starts out hot and blue. Over millions to billions of years, stars burn through their hydrogen fuel and evolve, eventually becoming cooler and redder. The presence of red stars means these galaxies didn't just form all their stars in a sudden burst, right when Webb observed them. They had already been forming stars for a long time before that. The stellar population models suggest these stars are hundreds of millions to over 1 billion years old. If the galaxy itself exists just 500 million years after the Big Bang, and it contains stars that are 1 billion years old, then those stars must have started forming before the Big Bang, which is obviously impossible. Let me pause here because I can feel some of you starting to doubt. Maybe you're thinking, okay, this sounds dramatic, but scientists make mistakes all the time. Surely there's some explanation that doesn't break physics. And you're right to think that way. Extraordinary claims require extraordinary evidence. So let me give you the specific names and studies that are causing this crisis in cosmology. In February 2023, a team led by Callum Dunn at the University of Edinburgh published a study in Monthly Notices of the Royal Astronomical Society analyzing Webb's observations of galaxy number densities at high redshift. They found that the number of bright galaxies at redshifts above Z equals 9 was 10 times higher than predicted by the standard models. 10 times. That's not a small discrepancy you can explain away with observational error. That's a fundamental mismatch between theory and reality. In July 2023, Harakanat et al. Published a study identifying galaxy candidates at redshifts up to Z equals 16, corresponding to just 250 million years after the Big Bang. These aren't just faint, distant blobs. Some of these galaxies are extraordinarily bright, with luminosities suggesting stellar masses far beyond what should be possible at such early times. One galaxy candidate, CEERS 93316, if confirmed at its suspected redshift of Z equals 16.7, would be the most distant and oldest galaxy ever observed. But more importantly, its brightness implies it contains nearly 1 billion solar masses of stars. 1 billion stars worth of mass, existing just 235 million years after the creation of the universe itself. In November 2023, the JADES collaboration, led by astronomers including Brent Robertson at UC Santa Cruz and Sandro Tacchella at the University of Cambridge, published spectroscopic confirmations of galaxies at extreme redshifts. Using Webb's NIR-SPEC instrument, they confirmed galaxies at Z equals 13.2, making them among the most distant objects ever spectroscopically verified. But confirmation wasn't the shocking part. The shocking part was the detailed analysis of what these galaxies are made of. The spectra show emission lines from oxygen and other heavy elements. Oxygen doesn't exist in the primordial universe. It's forged inside stars through nuclear fusion, then dispersed when those stars explode as supernova. The presence of oxygen means multiple generations of stars had already lived and died in these galaxies. The universe was supposed to be mostly pristine hydrogen at this point, with just the first generation of stars beginning to form. Instead, we're seeing evidence of stellar recycling, of chemical enrichment, of a cosmos that had already gone through significant evolution. Now, here's where it gets really interesting. A team led by Mike Boylan-Colchin at the University of Texas at Austin published a paper in Nature Astronomy with a title that captures the existential dread of modern cosmology, stress testing lambda CDM with high redshift galaxy candidates. In it, they carefully analyzed whether our standard model of cosmology could possibly produce the galaxies Webb is observing. Their conclusion was stark. To form galaxies this massive this early, you would need star formation efficiencies approaching 100%, and you would need it to happen in the very first generations of star formation. This violates everything we know about astrophysics. The first stars should be inefficient at forming because the primordial gas lacks heavy elements that help cool the gas and allow it to collapse. Without cooling, you can't form as many stars. It's a chicken and egg problem. You need stars to create heavy elements, and you need heavy elements to efficiently form stars. The early universe should be stuck in a low-efficiency mode until enough stellar generations have passed to enrich the gas. But Webb's observations suggest the universe somehow bypassed this bottleneck entirely. Every scientist I've mentioned, Lab, Donnan, Harakan, Robertson, Tacchella, Boylan-Colchin, these are not fringe researchers promoting wild theories. These are careful, conservative astronomers publishing in the most prestigious peer-reviewed journals in the world. They're not saying, we've disproven the Big Bang. They're saying, we found something that doesn't fit, and we don't know what it means yet. But the implications are unavoidable. Either our understanding of how galaxies form is catastrophically wrong, or our understanding of the universe's timeline is wrong, or something even stranger is happening. Let me make sure you're still with me, because we're about to go even deeper. The standard model of cosmology, called lambda CDM, is based on 6 fundamental parameters. These include the density of ordinary matter, the density of dark matter, the density of dark energy, the rate of expansion of the universe, the amplitude of primordial fluctuations, and the spectral index of those fluctuations. We've measured these parameters to incredible precision using the cosmic microwave background and other observations. When you plug these parameters into computer simulations and run them forward from the Big Bang to the present day, you get a universe that looks remarkably like the one we observe. Galaxies form, cluster together, evolve, and create the cosmic web of structure we see today. These simulations have been tested against thousands of observations, and they work. Until now. When you run those same simulations forward to the epoch when the universe was 200 to 500 million years old, they produce small, faint protogalaxies. They don't produce the massive, mature galaxies Webb is seeing. To make the simulations match Webb's observations, You have to change the parameters so dramatically that they no longer match all the other observations we've made. You break the cosmic microwave background predictions. You break the abundance of light elements. You break the large-scale structure of the universe. You can't fix one problem without creating 10 others. This is what's known in science as a paradigm crisis. It's what happened in physics in the early 1900s, when experiments started showing results that classical physics couldn't explain. The Michelson-Morley experiment showed that light didn't behave like a wave moving through a medium. The black body radiation spectrum couldn't be explained by classical thermodynamics. The photoelectric effect contradicted wave theory of light. Each problem individually could maybe be explained away, but collectively, they demanded a revolution. The resolution was quantum mechanics and relativity, two theories that completely redefined our understanding of reality. We might be at a similar moment right now in cosmology. The James Webb observations might be our Michelson-Morley moment, the first crack in a paradigm that's about to shatter. Before we continue, I need to address something. Some of you might be thinking, wait, does this mean the Big Bang never happened? Are we going back to a steady-state universe or some kind of eternal cosmos? Hold that thought. I want you to keep that question in your mind as we explore deeper, because the answer is far stranger than either option. But before we get there, we need to understand exactly what options cosmologists are considering. And to do that, we need to talk about what could possibly create galaxies that appear older than the universe itself. Drop a comment right now with the most shocking thing you've heard so far. I'm curious what's hitting you the hardest. One possibility is that we're simply misinterpreting the data. Maybe these aren't actually galaxies at all. Maybe they're quasars, extremely bright supermassive black holes that can mimic the appearance of galaxies. Or maybe they're gravitationally lensed images, where the light from a less distant galaxy is being magnified and distorted by a massive foreground object, making it appear brighter and more distant than it actually is. These are legitimate concerns, and astronomers have been carefully checking for them. The problem is that spectroscopic observations rule out most of these alternatives. When you break light down into its component wavelengths, you can identify specific emission and absorption lines that tell you what you're looking at. The spectra of these objects are consistent with galaxies, not quasars. They show the signature of stellar populations, not active black holes. And the distribution of these galaxies across the sky is too uniform to be explained by gravitational lensing, which would create clustered patterns. Could some of these candidates be misidentified? Absolutely. But all of them? That's statistically implausible. Another possibility is that our distance estimates are wrong. Redshift is our primary method for measuring cosmic distances, but it relies on understanding how the universe has expanded over time. If something about the expansion history is different than we think, then our redshift to distance conversions could be off. But here's the problem with that explanation. The expansion history of the universe is constrained by multiple independent observations. The cosmic microwave background tells us how the universe was expanding at 380,000 years after the Big Bang. Supernova observations tell us how the universe has been expanding over the past several billion years. Baryon acoustic oscillations, the clustering pattern of galaxies, give us additional constraints at intermediate times. All of these observations fit together into a consistent picture. To make the redshift distances wrong enough to solve the James Webb problem, you'd have to change the expansion history so much that you'd break all these other observations. You'd be fixing one problem by creating a dozen others. A third possibility, and this is where things get really interesting, is that star formation in the early universe was radically different than we've assumed. Maybe the first stars weren't the massive, short-lived population, 3 stars we've theorized. Maybe they were able to form more efficiently, or in greater numbers, or through processes we haven't considered. There's some theoretical support for this. Recent simulations have shown that in certain conditions, primordial gas can fragment into smaller clumps more readily than previously thought, potentially forming stars faster. A mechanism called supercompetitive accretion might allow gas to funnel into galaxies at extremely high rates in the early universe, building up stellar mass quickly. And maybe the first supermassive black holes, which Webb has also detected at surprisingly early times, played a role in triggering intense bursts of star formation through feedback effects we don't fully understand. But even pushing star formation models to their absolute limits, most theorists agree you can't account for all of what Webb is seeing. You might be able to explain some of the massive galaxies. You might be able to explain the bright galaxies. But explaining massive, bright, mature, chemically evolved galaxies at redshifts above 13? That requires something more radical. Which brings us to the fourth possibility, the one that's both terrifying and exhilarating for cosmologists. What if the Big Bang wasn't the beginning of everything? What if there was something before? Think of it like this. You wake up in a room with no memory of how you got there. You see a clock on the wall that says 3 p.m. You assume that's the current time and that your life began at some point before 3 p.m. today. But what if the clock is wrong? What if it was set to 3 p.m. when someone put it on the wall, but your life actually started days ago? The Big Bang is our cosmic clock, and we've been assuming it represents the absolute beginning of time. But what if it's just a transition point? A moment when the universe changed states, but not the ultimate origin of everything. This isn't just wild speculation. There are serious theoretical frameworks that allow for pre-Big Bang cosmologies. And this is where we're going next, into the realm of ideas that sound like science fiction, but are grounded in cutting-edge theoretical physics. If you're still with me, give this video a like. We're about to venture into territory that challenges not just our understanding of the universe's history, but the very nature of time, space, and existence itself. This is where cosmology meets philosophy, where mathematics meets metaphysics, and where the James Webb Space Telescope's observations might be pointing us toward a reality far stranger than anyone imagined. Let's talk about cosmic inflation. In the late 1970s and early 1980s, physicists realized that the standard Big Bang theory had some serious problems. One was called the horizon problem. The cosmic microwave background has almost exactly the same temperature in all directions, varying by less than 1 part in 100,000. But according to standard Big Bang cosmology, regions of space on opposite sides of the sky have never been in contact with each other. They've never had time to exchange heat and reach the same temperature because they're too far apart, and the universe isn't old enough for light to have traveled between them. So why are they the same temperature? It's like finding that every random person on Earth has exactly the same body temperature even though they've never met or communicated. How did they coordinate? Another problem was the flatness problem. The overall geometry of space can be curved, like the surface of a sphere, or negatively curved, like a saddle, or perfectly flat, like an infinite plane. Which geometry you get depends on the total density of matter and energy in the universe. Measurements show that our universe is flat, or extremely close to flat, to within 1%. But here's the thing. Flatness is an unstable equilibrium. If the universe started even slightly curved, the curvature would grow exponentially over time. For the universe to be as flat as it is today, the density in the early universe would have had to be fine-tuned to 1 part in 10 to the 60th power. That's a decimal point followed by 59 zeros and then a 1. Such precise fine-tuning seems absurdly unlikely unless something said it that way. The solution proposed by physicist Alan Guth in 1981 was cosmic inflation. Guth suggested that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, doubling in size every 10 to the negative 37 seconds or so. In less than a trillionth of a trillionth of a trillionth of a second, the universe grew from smaller than a proton to the size of a grapefruit or larger. This exponential expansion would solve both problems. The horizon problem is solved because the entire observable universe came from a tiny region that was small enough to have been in thermal contact before inflation began. Everything was at the same temperature, then inflation stretched that uniform region to cosmic scales. The flatness problem is solved because inflation stretches space so much that any initial curvature is diluted away, like how the surface of a balloon looks flatter the more you inflate it. Inflation has become the leading theory of the universe's earliest moments because it solves these problems and makes specific predictions that have been confirmed. It predicts that tiny quantum fluctuations in the inflating space would be stretched to cosmic scales and become the seeds of all cosmic structure, the slight density variations that eventually collapsed to form galaxies. It predicts a specific pattern to these fluctuations, which has been observed in the cosmic microwave background. It predicts that the universe should be spatially flat, which has been confirmed. Inflation works. But here's the catch. Inflation is driven by something called an inflated field, a hypothetical scalar field that permeates space. We don't know what this field is. We've never directly detected it. We just know that if it exists and has the right properties, it would cause inflation. And here's where things get weird. If inflation happened once, it's probably still happening somewhere. Think of inflation like boiling water. When you heat water, bubbles form where water transitions from liquid to gas. Those bubbles expand and eventually break the surface, creating the steam you see. Now imagine that space itself can be in different phases, different energy states. The inflated field is like the heat that keeps space in a high-energy, inflationary phase. When a region of space cools, the inflated field drops to a lower energy state, and inflation stops in that region. That region becomes a bubble universe, and inside that bubble, the energy released by the inflated field's transition becomes all the matter and radiation we observe. That transition is what we call the Big Bang. It's not the beginning of space and time. It's the moment when our region of space transitioned from an inflationary phase to a normal, expanding phase. But here's the mind-bending part. In the regions of space that haven't transitioned yet, inflation continues. And because inflation expands space exponentially fast, the inflating regions grow faster than bubble universes can form within them. This creates a situation called eternal inflation, proposed by physicist Alexander Velikin in 1983 and further developed by Andre Linde. In eternal inflation, bubble universes are constantly forming, each with its own Big Bang, but the inflating space between them grows faster than the bubbles form. The result is an infinite multiverse, an endless expanse of inflating space filled with countless bubble universes, each with its own physics, its own constants of nature, its own history. Our Big Bang wasn't the beginning of everything. It was the beginning of our bubble, our pocket of the larger multiverse. Now, you might be asking, what does this have to do with galaxies that appear older than the Big Bang? Here's the connection. If eternal inflation is real, then time itself becomes a slippery concept. In the inflating space between bubbles, time passes very differently than it does inside bubbles. An enormous amount of time might pass in the inflating region, while only a moment passes inside a bubble, or vice versa. More importantly, the concept of a beginning of time zero becomes ambiguous. When did the multiverse begin? Did it begin at all? Or has it existed eternally into the past, with no starting point? These aren't just philosophical questions. They have observable consequences. If our bubble universe formed from a larger, older multiverse, then there might be remnants, echoes, or influences from that larger structure. There might be patterns in the cosmic microwave background that carry information from before our Big Bang. And if matter or structures could somehow exist in the inflating region, or if there are ways for information or influence to propagate between bubbles, then we might observe things that appear older than our local Big Bang. Not because they're older than the beginning of everything, but because they're older than the beginning of our particular bubble. Let me give you an analogy. Imagine you're born on a ship at sea. You've never seen land. To you, the ship is the entire universe. Someone asks you, when did the universe begin? You might answer, well, this ship was built 10 years ago, so the universe is 10 years old. But unbeknownst to you, there's a whole world outside your ship. There are continents, cities, civilizations that have existed for thousands of years. If you suddenly discovered a 500-year-old artifact on your ship, perhaps washed aboard during a storm, you'd be confused. This object is 50 times older than the universe you know. But it's not older than the larger world beyond your ship. It just came from a part of reality you didn't know existed. The James Webb observations might be our 500-year-old artifact. They might be telling us that our observable universe, our bubble, is not the entirety of reality. There's a larger, older structure out there, and we're just seeing hints of it. But eternal inflation isn't the only framework that allows for a pre-Big Bang cosmology. Another comes from string theory and a concept called the ekpyrotic universe. String theory, as you may know, proposes that the fundamental constituents of reality aren't particles but tiny, vibrating strings of energy. Different vibrational modes of these strings correspond to different particles. For string theory to be mathematically consistent, it requires extra dimensions of space beyond the 3 we experience. Most formulations require 10 or 11 total dimensions. The extra dimensions are thought to be compactified, curled up so small that we don't notice them in everyday life. But in the early universe, or in extreme conditions, these extra dimensions might behave very differently. One version of string theory, called M-theory, suggests that our universe might be a 3-dimensional membrane, or brain, floating in a higher dimensional space. There might be other brains out there, other universes, existing parallel to ours in the extra dimensions. In 2001, physicists Paul Steinhardt and Neil Turok proposed the ekpyrotic model, in which our Big Bang was caused by a collision between two brains. Picture two parallel membranes floating in higher dimensional space. They're attracted to each other by forces mediated through the extra dimensions. Eventually, they collide. The collision releases enormous energy, which manifests in our brain as the hot, dense state we call the Big Bang. The matter and radiation in our universe are the result of kinetic energy from the collision being converted into particles. After the collision, the brains bounce apart, that are pulled back together by the attractive forces, leading to another collision, another Big Bang. This cycle repeats eternally, creating a cyclic cosmology where the universe goes through endless cycles of expansion, contraction, collision, and rebirth. In the ekpyrotic model, time doesn't begin at the Big Bang. It extends infinitely into the past and future. Each Big Bang is a transition point, a reset of our brain's state, but not a beginning of time itself. The universe is eternal, but it goes through periodic reinitializations. Now, if this model is correct, what would happen to structures that existed before a collision? In most versions, everything is essentially erased. The collision is so energetic that all previous matter and structure are destroyed and converted back into primordial energy. But Steinhardt, Turok, and others have explored variations where some information might survive from one cycle to the next. Perhaps patterns in the distribution of matter, or ripples in spacetime, or even structures in the extra dimensions could persist through a collision and influence the next cycle. If so, we might observe relics from a previous cycle, objects or patterns that are, in a sense, older than our current Big Bang. There's also a third framework, coming from quantum cosmology and the work of physicists like Roger Penrose. Penrose has proposed a model called Conformal cyclic cosmology, or CCC. This one's wild. Penrose starts from the observation that the early universe was in an extremely low entropy state. Entropy is a measure of disorder, and the second law of thermodynamics says entropy always increases. So the universe started in an incredibly ordered state and has been becoming more disordered ever since. But why? Why did the universe start with such low entropy? That's a deep mystery. Penrose suggests that the answer lies in understanding what happens at the far future of the universe. In the distant future, trillions upon trillions of years from now, all stars will have burned out, all black holes will have evaporated through Hawking radiation, and the universe will consist of nothing but a thin, cold gas of photons and other massless particles expanding forever. This is called the heat death of the universe. But here's Penrose's insight. In that far future state, with no massive particles and no structures left, there's no meaningful way to measure time or scale. Without clocks or rulers made of atoms, the concepts of time intervals and distances become ambiguous. Mathematically, Penrose argues you can perform a transformation called a conformal rescaling that essentially equates the infinite far future of one universe, called an eon, with the Big Bang beginning of the next eon. The end of one universe is the beginning of the next. Time becomes cyclic, but in a strange way, where the infinite future of one phase transitions into the finite beginning of another phase. In CCC, information can potentially pass from one eon to the next. Penrose has even claimed to find evidence of this in the cosmic microwave background. He's identified circular patterns that he interprets as the signatures of collisions between supermassive black holes in the previous eon, imprinted somehow into the structure of spacetime and carried through the transition into our eon. These claims are controversial, and most cosmologists remain skeptical, but the model is mathematically rigorous and can't be easily dismissed. If CCC is correct, then the Big Bang wasn't the beginning. It was a transition from a previous phase of existence. And structures, patterns, or even objects from the previous eon might have left traces that we can observe today. Now, let me tie this back to the James Webb observations. If any of these pre-Big Bang cosmologies, eternal inflation, ekpyrotic collisions, or conformal cyclic cosmology, are correct, then the universe has a history that extends before we call the Big Bang. That earlier history might have allowed structures to form, evolve, and somehow persist or influence our current era. The galaxies Webb is observing might not be older than the ultimate beginning of everything, because there is no ultimate beginning. They might simply be older than the most recent transition event, the moment we mistakenly call the beginning of time, because it's the beginning of our observable universe's current phase. This doesn't mean the Big Bang didn't happen. It means the Big Bang is a chapter in a much longer story, not the opening sentence. I want to pause and make sure you're grasping the magnitude of what we're discussing. For nearly a century, cosmology has been built on the assumption that the Big Bang was the beginning, the moment of creation, time zero. Everything we've observed has been interpreted through that lens. But the James Webb Space Telescope is now showing us observations that strain that interpretation to the breaking point. We're being forced to confront the possibility that the story we've been telling ourselves about cosmic history is incomplete. And that incompleteness isn't a small footnote. It's a fundamental misunderstanding of the nature of time, existence, and origins. The universe might not have a beginning at all, or if it does, that beginning might be so far removed from the Big Bang that everything we thought we knew is just a tiny fragment of a much grander narrative. Before we go further into the implications, I need you to do something. Right now, share this video with someone who thinks they understand how the universe works. Share it with that friend who's always confident they have everything figured out. Because what we're about to explore next is going to challenge not just scientific understanding, but the very foundations of how we think about reality. And we need more people wrestling with these questions. Let's talk about what happens when you take these pre-Big Bang cosmologies seriously and try to make specific predictions. Because that's what separates science from philosophy, the ability to make testable predictions that can be confirmed or refuted by observation. If the universe went through cycles, or if our Big Bang emerged from eternal inflation, or if we're one bubble in a vast multiverse, what would we expect to see? And critically, do the James Webb observations match any of those predictions? In eternal inflation, each bubble universe nucleates with potentially different physical constants. The strength of gravity, the mass of the electron, the speed of light, all of these could vary from bubble to bubble, depending on how the fields that determine these constants settle into their lowest energy states. This is related to the landscape problem in string theory, the fact that there are an estimated 10 to the 500 power different possible vacuum states, each corresponding to a different possible universe with different laws of physics. Most of these universes would be utterly inhospitable to life. In some, stars could never form. In others, atoms would be unstable. The fact that we observe a universe so finely tuned for complexity and life is explained anthropically. We exist in one of the rare bubbles where the constants allow for our existence because we couldn't exist anywhere else to observe it. But here's the interesting part. If bubble universes can interact, even weakly, then we might see evidence of other bubbles. In 2010, a team led by Stephen Feeney at University College London claimed to find evidence in the cosmic microwave background of 4 circular patterns that could be the signatures of our bubble colliding with neighboring bubbles. When 2 bubbles collide, the collision would create a shockwave that propagates through both bubbles. In our bubble, this shockwave would appear as a circular pattern of temperature fluctuations in the cosmic microwave background, centered on the direction of the collision. The claim was controversial and hasn't been confirmed by subsequent analyses, but it illustrates the kind of signature we'd be looking for. More relevant to the James Webb observations, if our bubble formed relatively recently in the eternal inflation process, and if information or matter from the larger inflating region could somehow influence our bubble's early moments, then we might see structures that don't fit the standard timeline. They wouldn't be older than the beginning of everything, but they'd be older than the beginning of our bubble, or they'd carry information from the pre-bubble state that allowed them to form faster than standard physics would allow. In ekpyrotic and cyclic cosmologies, each cycle begins with a collision that creates a hot, dense state. But the collision isn't perfectly uniform. There are ripples, perturbations created by quantum fluctuations in the fields that drive the collision. These perturbations become the density fluctuations that seed structure formation. Critically, some versions of ekpyrotic cosmology predict that these perturbations have slightly different statistical properties than the perturbations predicted by standard inflation. Specifically, they might have more power on small scales, meaning more structure on small physical scales. This could potentially lead to earlier and more efficient formation of the first stars and galaxies. If the ekpyrotic model is correct, and if the collision that birthed our current cycle had particular properties, it's conceivable that galaxies could form faster and larger than standard inflation models predict. The James Webb observations of massive early galaxies might be evidence for this alternative initial condition. A hint that our Big Bang was a collision event rather than an inflationary beginning. Penrose's conformal cyclic cosmology makes an even more specific prediction. Penrose argues that certain structures from the previous eon, specifically the gravitational waves produced by the inspiral and merger of supermassive black holes, could leave an imprint on the cosmic microwave background of the next eon. He calls these Hawking points because they're related to the Hawking radiation emitted by the black holes as they evaporate. In several papers published between 2010 and 2020, Penrose and his collaborators claim to identify these Hawking points in the actual cosmic microwave background data. They found circular patterns of concentric temperature rings that matched the predicted signature. The mainstream cosmology community has been skeptical, arguing that similar patterns can arise by chance in random data. But Penrose maintains that the number and distribution of these patterns is too significant to dismiss as coincidence. If he's right, we're seeing direct evidence that the universe existed before the Big Bang, that there was a previous eon, and that its most dramatic events the deaths of its largest black holes left scars that propagated into our time. Now, let me bring this back to the specific problem the James Webb Space Telescope has created. None of these pre-Big Bang cosmologies, as currently formulated, explicitly predict that we should see fully formed spiral galaxies at redshifts above 13. They weren't designed to explain that. They were developed to solve other problems, like the arrow of time, the fine-tuning of physical constants, and the quantum origin of structure. But what they do provide is a framework in which the Big Bang is not an absolute beginning, and in which the conditions immediately after the Big Bang might have been influenced by prior states or events. This opens the door to explanations for the Webb observations that would be impossible in a standard cosmology, where the Big Bang is the ultimate beginning. For example, if our observable universe emerged from a region of eternal inflation that had been inflating for an enormous amount of time, that prior inflation might have processed matter and energy in ways we don't understand, creating precursor structures or fields that gave our universe a head start on galaxy formation. Or if the Big Bang was a brain collision in the ekpyrotic model, perhaps some structures from the colliding brains weren't completely destroyed, but were instead compressed and recycled into the new cycle, serving as seeds for rapid galaxy formation. Or in CCC, perhaps information about matter distributions from the previous eon influenced how matter clustered in our eon, creating an abnormally rapid formation process. These are speculative ideas, but they're grounded in serious theoretical frameworks. They're not ad hoc. They follow from models that were developed for independent reasons and that make other testable predictions. But I want to be completely honest with you about where the science stands right now. The mainstream interpretation among cosmologists is still that we don't need to invoke pre-Big Bang cosmologies to explain the James Webb observations. The consensus view is that we're probably seeing some combination of factors: higher star formation efficiencies than expected, contributions from early supermassive black holes that create bright quasar-like emission, and possibly some observational systematics we haven't fully accounted for. A significant number of the most extreme high redshift galaxy candidates identified in Webb's first year have not yet been spectroscopically confirmed. Redshifts estimated from photometry, looking at the overall color of an object, can be misleading. Some of these candidates might turn out to be closer and less extreme when proper spectroscopy is done. The problem might shrink as we gather more data. However, and this is critical, the problem isn't going away. As of mid-2024, we now have spectroscopic confirmation of numerous galaxies at redshifts above 10. Including several above 12 and 13. These are definitely real, definitely distant, and definitely massive. The Lab et al. Study I mentioned earlier used spectroscopy. The JADES collaboration's results are spectroscopic. We're not talking about ambiguous candidates anymore. We're talking about confirmed observations that challenge our models. And the number of such galaxies keeps growing as Webb continues its survey work. With each new deep field observation, we find more massive early galaxies. The problem is real, it's persistent, and it's forcing cosmologists to seriously reconsider assumptions that have been bedrock for decades. Let me give you a sense of how the community is responding. In May 2023, a workshop was held at the Kavli Institute for Theoretical Physics at UC Santa Barbara, titled Galaxies in the Epoch of Reionization, Predictions and Observations. Leading theorists and observers gathered to reconcile the tension between models and Webb's data. The discussions were intense. Some researchers argued for modifications to star formation physics. Others advocated for changes to how we model dark matter clustering. A few brave souls suggested that we might need to revisit the cosmological parameters themselves, perhaps adjusting the amplitude of primordial fluctuations or reconsidering the nature of dark energy. But there was also an undercurrent of something deeper, a recognition that we might be seeing the first hints of new physics, something beyond the standard model of cosmology. Several talks explored the possibility that early dark energy, a hypothetical form of dark energy that existed in the early universe, but has since decayed away, might have accelerated the formation of structure. Others discussed whether modifications to gravity on cosmic scales could enhance the growth of structure. And yes, some talks touched on pre-Big Bang scenarios, though cautiously, as these remain speculative. The point is that the scientific community is not ignoring this. The James Webb observations have triggered a genuine crisis, in the original sense of the word, a decision point where the field must choose a direction. Either we find a way to modify our existing models to accommodate the observations, which will require significant revisions to well-established astrophysics, or we consider more radical alternatives that challenge the very framework of Big Bang cosmology. Both paths are uncomfortable. Science advances by being conservative, by not overthrowing established theories unless absolutely necessary. But science also advances by being honest, by following the evidence wherever it leads. And right now, the evidence is leading toward very uncomfortable territory. Let me shift gears and talk about what all of this means for you personally. Because this isn't just an academic debate happening in journals and conferences. This is a fundamental question about the nature of existence, and the answer has implications for how you understand your place in reality. Stay with me because we're about to explore why this matters on a human level, not just a cosmic one. Think about how you've been taught to understand time. You probably think of time as a line stretching from the past to the present into the future. There's a direction to it, an arrow. Things happen in sequence. Causes precede effects. And somewhere far in the past, there's a beginning point, a moment before which nothing existed. This is such a deeply ingrained intuition that it's hard to imagine any alternative. But what the James Webb observations might be telling us is that this intuition is wrong. Time might not have a beginning. Or if it does, that beginning might be so radically different from what we've imagined that the word beginning becomes meaningless. Consider what it means to exist in a universe that has no beginning. In such a universe, every moment is embedded in an infinite chain of prior causes. There is no first cause, no ultimate origin. Things are the way they are because of what came before, and what came before was shaped by what came before that in an infinite regress. This idea terrifies some people and exhilarates others. For the terrified, it removes the comfort of a clear origin story, a moment of creation that gives existence a defined starting point. For the exhilarated, it solves the problem of asking what caused the beginning, because there is no beginning to explain. Both reactions are valid. Both reflect deep human needs for either certainty or infinite possibility. Or consider the alternative, that we exist in a multiverse, one bubble among countless others, each with its own Big Bang, its own history, its own physics. In this scenario, the universe you observe, everything you can ever see or measure, is a tiny fraction of what exists. There are other universes, perhaps infinite in number, where the laws of physics are different, where stars never formed, or where intelligent life evolved in ways utterly alien to us. In most of these universes, you couldn't exist. The constants aren't right. But in this universe, in this bubble, conditions happen to be perfect for complexity, for stars and planets and life and consciousness. You exist because of an anthropic selection effect. You're here because you couldn't be anywhere else. Is that comforting or disturbing? Does it make your existence feel improbable and precious, or contingent and arbitrary? These aren't idle philosophical musings. How you answer these questions affects how you live your life. If the universe is eternal, with no ultimate beginning or end, then the present moment is all that truly exists. The past is gone, the future uncertain, and the infinite regress of prior causes is beyond your concern. This can be liberating. It focuses you on the here and now, on making the most of the existence you have. But it can also feel vertiginous, like standing on an edge with no ground beneath you. If there's no ultimate foundation to reality, no bedrock of certainty, then everything floats free, unanchored. Some find freedom in that. Others find terror. If we live in a multiverse, one bubble among infinite others, then the question of why this universe has the properties it does becomes meaningless. It has these properties by chance, and we observe them because we couldn't exist in bubbles where the properties were different. This can feel like a cop-out, an explanation that explains nothing. But it also shifts your focus. Instead of asking, why is the universe this way? You ask, what can I do within this universe? It's a shift from cosmic why to personal how, and that shift can be empowering. You stop waiting for the universe to tell you your purpose and start creating your own. If the universe cycles, dying and being reborn, then nothing is truly permanent, but nothing is truly lost either. Every ending is a beginning. Every death feeds new life. This can provide comfort in the face of mortality. You might die, your civilization might end, the stars might burn out, but the story continues. The universe will be born again, and the matter that once was you will become something else. Participant in a story that never truly ends. Or it can feel futile. If everything is eventually erased and recycled, do your actions matter? Does anything you do persist? I'm dwelling on these personal implications because I want you to feel the weight of what's at stake. The James Webb Space Telescope isn't just providing data for scientists to puzzle over. It's providing information that changes the existential landscape for all of us. We're learning that the universe is stranger, older, and more complex than we thought. And that knowledge changes us. It changes how we see ourselves, how we see our place in the cosmos, how we think about meaning and purpose. This is why science matters, not just for the technologies it enables, but for the perspectives it offers, for the way it expands our sense of what's possible and real. Now, let me bring up something that might be bothering you. You might be thinking, okay, but even if the Big Bang wasn't the absolute beginning, even if there were prior states or cycles or other bubbles, doesn't that just push the question back? Where did the eternal inflation come from? Where did the ekpyrotic brains come from? Where did the first eon come from? You haven't solved the problem of origins. You've just moved it. And you're absolutely right. That is the correct objection. Let me address it head-on because it leads us to perhaps the deepest question in all of cosmology, and it's where physics, philosophy, and theology converge. The question is, why is there something rather than nothing? This is the ultimate mystery, the one that haunts every cosmological theory. Even if the universe is eternal, even if it has no beginning, you can still ask why it exists at all. Why does eternal inflation happen? Why do brains exist? Why are there laws of physics? Why is there a multiverse? Every scientific explanation assumes the existence of something, some prior framework or laws or fields. Science is incredibly good at explaining how things happen, given that something exists. But science struggles with the question of why anything exists in the first place. There are basically three philosophical positions you can take on this question. The first is that existence is a brute fact. It simply is, and there's no deeper explanation. Asking, why does something exist, is like asking, what's north of the North Pole? It's a category error, a question that sounds meaningful, but actually isn't, because it presupposes there should be an explanation when there might not be. Things exist because they do. And that's the end of it. This position is unsatisfying to many people because it feels like giving up, like refusing to ask the deepest question. But it might be correct. Maybe there is no why. Maybe existence is self-explanatory or beyond explanation. The second position is that existence is necessary. Perhaps the universe or multiverse or whatever the ultimate framework is exists because it must exist. There's something about the structure of logic or mathematics or the laws of physics that makes existence inevitable. This is the position taken by some physicists and philosophers. Stephen Hawking, in his book The Grand Design, suggested that the laws of quantum mechanics might require the universe to create itself from nothing. Alexander Velikin has proposed that in quantum cosmology, universes can tunnel into existence from literally nothing, a state with no space, no time, no matter, no fields. The mathematics of quantum mechanics allows for this. Whether it's the right interpretation is another question. But if existence is necessary, if the laws of logic or quantum mechanics or some deeper principle require that something exist, then the question is answered. There's something rather than nothing, because nothing is unstable, or impossible, or in some sense, less fundamental than something. The third position is that existence has a purpose, a reason, that there's an intentionality or teleology behind why things are. This is the traditional religious answer, that God or some creative principle willed the universe into being. Science can't address this position directly, because science deals with physical causes, not purposes or intentions. You can't run an experiment to test for divine intention. But you also can't rule it out scientifically. If the universe was created with a purpose, and if that creation looks, from the inside, like it follows natural laws, then science would observe exactly what it observes. A universe that behaves according to consistent principles, but whose ultimate origin remains mysterious. I'm not advocating for this position. I'm just noting that it's philosophically coherent, and that the James Webb observations don't favor or disfavor it. Whether the Big Bang was the beginning or just a transition point, whether the universe is 13.8 billion years old or eternal, the question of why there's anything at all remains open. What I find fascinating is that the pre-Big Bang cosmologies we've discussed, eternal inflation, periodic cycles, conformal cyclic cosmology, all lean toward either the brute fact position or the necessary existence position. They suggest that existence might be eternal, with no beginning, which aligns with the brute fact view. Or they suggest that the laws governing existence, quantum mechanics, string theory, create conditions where universes inevitably form, which aligns with the necessary existence view. The Big Bang in these frameworks loses its status as the moment of creation and becomes just a transition, a phase change in an ongoing process. This shift is profound. It moves cosmology away from asking about origins and toward asking about processes, away from beginnings and toward dynamics. It's a shift from how did everything start to how does everything work. And here's why that matters for understanding the James Webb observations. If the Big Bang is just a transition, then the timeline of our observable universe, the 13.8 billion years we confidently assert, is not the full story. It's the time since the transition, not the time since the beginning of being. Structures that appear to be older than 13.8 billion years, or that appear to require more than 13.8 billion years to form, aren't paradoxes. They're hints that the story is longer and more complex than we thought. They're evidence that the universe has a history that predates what we call the Big Bang. And that history, whatever it is, provided initial conditions that allowed galaxies to form faster, or structures to persist from prior states, or matter to cluster more efficiently than standard cosmology assumes. Let me give you a concrete example of how this might work. Imagine that before our Big Bang, during a prior phase of inflation, or in a previous cycle, density fluctuations in the quantum fields created regions of slightly higher or lower density. These fluctuations are normally erased or smoothed out by inflation. But suppose some survived, perhaps imprinted in the fabric of spacetime itself. When our Big Bang occurred, these pre-existing fluctuations would serve as additional seeds for structure formation, on top of the fluctuations generated during our local inflationary period. The result would be more structure, or structure that forms faster, because it had a head start. The galaxy's web is observing might be growing from these enhanced seeds. structures that benefited from information or initial conditions carried over from a pre-Big Bang state. This is speculation, of course. We don't have a detailed, worked-out theory of how this would happen, but it's the kind of speculation that serious physicists are now engaging in, not because they want to overthrow the Big Bang, but because the observations demand explanation, and the standard model isn't providing one. The beauty of science is that it's self-correcting. When observations don't match theory, either the observations are wrong, which requires demonstrating observational error, or the theory is wrong, which requires proposing a better theory. Right now, the observations seem solid. The spectroscopy is confirming what the imaging suggested. The galaxies are real, they're distant, and they're massive. So the focus is shifting toward the theory. What modifications, extensions, or alternatives can we propose that explain the observations while preserving everything else we know? This is the stage we're at right now. We're in the early days of a paradigm shift. The old paradigm, the simple Big Bang with a clear timeline, is showing cracks. The new paradigm hasn't fully emerged yet. We have candidate theories, eternal inflation, ekpyrotic cosmology, conformal cyclic cosmology, modifications to star formation, early dark energy, but we don't yet know which, if any, is correct. Over the next decade, as Webb continues to observe and as new telescopes come online, we'll gather more data. We'll refine our understanding. We'll test predictions. And gradually, a new consensus will form. But right now, we're in the exciting, disorienting phase where everything is uncertain and anything seems possible. Let me tell you what's coming next in our journey through this cosmic mystery. We're about to explore the specific mechanisms that could allow galaxies to form faster than we thought possible. We're going to dive into the physics of dark matter, supermassive black holes, and the first stars. We're going to look at cutting-edge simulations that are trying to reproduce what Webb is seeing. And we're going to examine alternative theories that challenge not just the timeline of the Big Bang, but the fundamental assumptions of cosmology itself. This is where we go from what did Webb see to how could it possibly work? From observation to mechanism, from mystery to hypothesis. If you're still with me, drop a comment with your wildest theory about what's going on. I'm genuinely curious what ideas you're coming up with. And make sure you've liked and subscribed because we're just getting started. So let's talk about dark matter. Dark matter is one of the most well-established components of modern cosmology, even though we still don't know what it actually is. We know it exists because of its gravitational effects. Galaxies rotate faster than they should if only visible matter were present. Galaxy clusters contain far more mass than we can see in stars and gas. The cosmic microwave background fluctuations require a component of matter that doesn't interact with light. Gravitational lensing observations show mass bending space in places where we see nothing. All of this evidence points to the existence of matter that we can't see directly, matter that doesn't emit, absorb, or scatter light. We call it dark matter, and it makes up about 85% of all the matter in the universe. The remaining 15% is ordinary matter, the stuff that makes up stars, planets, and us. Dark matter plays a crucial role in structure formation. In the early universe, after the Big Bang and the end of inflation, matter was distributed nearly uniformly, with only tiny density fluctuations, about 1 part in 100,000. These fluctuations were the seeds of all cosmic structure. Regions that were slightly denser than average had slightly stronger gravity, which pulled in more matter, making them even denser, which increased their gravity further in a feedback loop called gravitational instability. Over time, these overdense regions collapsed to form the first structures, dark matter halos, regions where dark matter concentrated gravitationally. Ordinary matter, hydrogen and helium gas, fell into these dark matter halos and was pulled toward their centers. When the gas became dense enough and hot enough, nuclear fusion ignited, forming the first stars. These stars gathered into the first galaxies. The key point is that dark matter provides the gravitational scaffolding for structure formation. Without dark matter, there wouldn't have been enough gravity to pull ordinary matter together quickly enough to form galaxies. The universe would have remained mostly smooth and featureless for billions of years longer. Dark matter accelerates structure formation because it can start collapsing earlier than ordinary matter. Ordinary matter is coupled to photons, light, before recombination. This coupling prevents it from collapsing because the pressure from the photons pushes it outward. But dark matter doesn't interact with photons. It can start collapsing as soon as inflation ends, giving it a head start of 380,000 years. By the time ordinary matter is free to collapse, the dark matter has already formed halos, and the ordinary matter just falls into them. Now, here's the critical question for the James Webb observations. Could dark matter be clumpier than we thought? Could there be more dark matter in certain regions? Or could dark matter have properties that make it collapse faster, creating deeper gravitational wells earlier, which would allow galaxies to form more quickly? This is one of the leading explanations being explored. The standard model assumes that dark matter is cold, meaning its particles move slowly, not at relativistic speeds. This is called cold dark matter, or CDM, the CDM in lambda CDM. Cold dark matter forms structure bottom-up, with small halos forming first and merging to create larger ones over time. But what if dark matter is not perfectly cold? What if it has some small amount of self-interaction, where dark matter particles occasionally scatter off each other? Or what if dark matter particles have a small but non-zero temperature, making it warm dark matter instead of cold? These modifications would change how quickly and efficiently dark matter halos form, potentially accelerating the formation of the first galaxies. There's also the possibility of primordial black holes. Primordial black holes are a hypothetical form of black hole that would have formed in the first fraction of a second after the Big Bang, not from the collapse of stars, but from the direct collapse of overdense regions in the primordial plasma. If primordial black holes exist and make up some fraction of the dark matter, they could serve as seeds for rapid galaxy formation. A primordial black hole sitting in the early universe would gravitationally attract surrounding gas, creating an accretion disk. The infalling gas would heat up and emit radiation, which could trigger star formation in the surrounding material. A single massive primordial black hole could potentially trigger the formation of an entire galaxy around it in a much shorter time than the standard bottom-up process would allow. This idea connects to another mystery that Webb has uncovered: the existence of supermassive black holes at extremely early times. In addition to finding massive galaxies at high redshift, Webb has also detected quasars, extremely luminous objects powered by supermassive black holes at redshifts above 7 and even above 10. These black holes have masses of millions to billions of times the mass of the Sun. The problem is that we don't understand how black holes can grow that large that quickly. Black holes grow by accreting matter, pulling in gas and stars from their surroundings. But there's a limit to how fast they can grow, called the Eddington limit. When a black hole is actively feeding, the infalling matter heats up and emits radiation. This radiation exerts outward pressure on the surrounding gas, which counteracts the inward pull of gravity. If a black hole tries to eat too fast, the radiation pressure blows away the gas, shutting off the food supply. The Eddington limit sets the maximum accretion rate. Given the Eddington limit, to grow a billion solar mass black hole, you need to start with a seed black hole and give it time to feed. If you start with a seed black hole of 100 solar masses, which might form from the collapse of one of the first stars, it would take about 700 million years of continuous feeding at the Eddington limit to reach a billion solar masses. But Webb is finding billion solar mass black holes at times when the universe was only 500 to 600 million years old. That doesn't leave enough time. Even if the black hole formed immediately after the Big Bang and fed continuously at the maximum rate. So other black holes can somehow exceed the Eddington limit, feeding super Eddington through processes we don't understand, or they start from much larger seeds. Primordial black holes could be those larger seeds. If 1,000 or 10,000 solar mass primordial black hole existed from the very beginning, it would have a much easier time growing to 1 billion solar masses within the available time. And here's where this ties back to rapid galaxy formation. Supermassive black holes and galaxies co-evolve. There's a tight relationship between the mass of the central supermassive black hole in a galaxy and the mass of the galaxy's bulge, the central concentration of stars. This suggests that the black hole and the galaxy grow together, influencing each other. The black hole feeds on gas, which releases energy that heats the surrounding gas, which can either trigger star formation by compressing gas clouds or suppress star formation by blowing gas out of the galaxy. This feedback process is complex, but the key point is that a supermassive black hole can dramatically affect how efficiently a galaxy forms stars. If supermassive black holes formed early, perhaps from primordial black hole seeds, they could have triggered intense bursts of star formation in their host galaxies, creating the massive galaxies Webb is observing. This is one of the most promising conventional explanations for the Webb observations. It doesn't require pre-Big Bang cosmologies or changes to fundamental physics. It requires assuming that primordial black holes exist, that they're massive enough to serve as seeds, and that the feedback between black holes and star formation is more efficient in the early universe than in the nearby universe. These are big assumptions, but they're testable. If this explanation is correct, then the massive early galaxies should be closely associated with active supermassive black holes. Webb should detect the signatures of both, stellar light from the galaxy and energetic radiation from the accreting black hole. And indeed, some of the massive early galaxies Webb has found do show signs of active black holes. The story is complex, and the data is still being analyzed, but the correlation is there. Now, let me introduce another layer of complexity. The first stars, those population 3 stars I mentioned earlier, were very different from stars today. They formed from pure hydrogen and helium, with no heavy elements. The lack of heavy elements matters, because heavy elements are very efficient at cooling gas. When gas cools, it can contract more easily under gravity, fragmenting into smaller clumps that become individual stars. Without heavy elements, the primordial gas couldn't cool as efficiently, so it tended to form much larger clumps. The first stars were therefore much more massive than typical stars today. Estimates suggest they had masses of 50 to 300 times the mass of the Sun, compared to the Sun's 1 solar mass, or the typical star mass of about 0.2 solar masses. These massive first stars had profound effects. They burned through their fuel incredibly quickly, living only a few million years before exploding as supernova. When they exploded, they dispersed the heavy elements they'd forged through fusion throughout their surroundings, enriching the gas and allowing the next generation of stars to form more efficiently. They also emitted intense ultraviolet radiation that ionized the hydrogen in the surrounding universe, creating bubbles of ionized gas that gradually merged and reionized the entire universe. This epoch of reionization occurred between about 200 million and 1 billion years after the Big Bang, and it's one of the key transitions in cosmic history. But here's the interesting part. If the first stars were extremely massive, they would have also formed black holes when they died. A star with more than about 25 solar masses will collapse into a black hole when its core runs out of fuel, rather than exploding completely. So the first generation of stars would have created a population of black holes with masses of tens to hundreds of solar masses. These black holes could merge with each other, growing larger, or they could accrete gas and grow that way. Over time, they could become the seeds of the supermassive black holes we observe today. This provides another pathway to early supermassive black holes, complementary to the primordial black hole idea. Moreover, if the first stars formed in particularly dense environments, perhaps in regions that benefited from pre-Big Bang density fluctuations, as I speculated earlier, they might have formed in tighter clusters than we expect. A dense cluster of massive stars would evolve rapidly, creating a swarm of black holes in a small region. These black holes could merge repeatedly through dynamical interactions, creating intermediate mass black holes of thousands to tens of thousands of solar masses within just a few tens of millions of years. These intermediate mass black holes could then serve as the seeds for the supermassive black holes and the massive galaxies. The entire process could happen much faster than in the standard scenario, where structure forms slowly from the bottom up. I want to emphasize that all of this primordial black holes, super Eddington accretion, dense clusters of massive first stars, is highly speculative, but grounded in physics we understand. These mechanisms don't require new laws of physics. They require conditions in the early universe to be somewhat different than the average conditions we've been assuming. And that's the key. Our models of the early universe have been based on average conditions, typical density fluctuations, typical environments. But the universe isn't uniform. There are regions that are denser than average, regions where fluctuations happen to line up constructively, creating pockets of rapid evolution. The galaxy's web is observing might be forming in these special regions, the cosmic equivalents of hotspots where everything happens faster. But there's a problem with this explanation. If these are just rare, atypical regions, then we shouldn't be finding so many of them. Remember the Donnan et al. Study I mentioned earlier? They found that the number of bright galaxies at high redshift was 10 times higher than predicted. If massive early galaxies only formed in rare, special environments, we'd expect to find a few, not dozens or hundreds. The fact that they seem relatively common suggests that something more systematic is going on, not just rare statistical flukes. Either the conditions in the early universe were more favorable for rapid galaxy formation than we thought across the board, or there's some physical process we're missing entirely. This brings us back to the idea that the initial conditions themselves, the state of the universe immediately after the Big Bang, might have been different than the standard model assumes. And this is where pre-Big Bang cosmologies become relevant again. If our Big Bang emerged from a prior state, whether that's eternal inflation, a brane collision, or a previous eon, then the initial conditions might carry signatures or biases from that prior state. The density fluctuations might be stronger than expected, or distributed differently, or seeded by structures that partially survived the transition. The universe might have started with more small-scale structure than our models assume, giving galaxy formation a significant head start. Let me walk you through a specific scenario to make this concrete. Imagine that our universe emerged from a collision between two branes in the ekpyrotic model. During the collision, the kinetic energy of the branes converts into matter and radiation, creating the hot dense state we call the Big Bang. But the collision isn't perfectly smooth. There are ripples, wrinkles in the branes caused by quantum fluctuations or by structures that existed on the branes before the collision. These wrinkles create variations in how much energy gets deposited in different regions. Some regions get more energy, others get less. These variations become density fluctuations in the newborn universe, but they're not the same as the fluctuations predicted by standard inflation. They might be stronger or have different statistical properties, or be correlated across different scales in unusual ways. Now, add dark matter to the picture. Dark matter would have been created in the collision as well, perhaps as some kind of exotic particle produced by the high-energy physics of the brane collision. This dark matter immediately begins to cluster gravitationally in the regions of higher density created by the brane wrinkles. Because these density fluctuations are stronger than in the standard scenario, the dark matter clustering happens faster. Within just 10 or 20 million years after the collision, significant dark matter halos have already formed. When ordinary matter decouples from radiation at 380,000 years, it falls into these pre-existing, already mature dark matter halos. The gas collapses rapidly, and the first stars begin forming not at 100 or 200 million years, but at 50 or 100 million years. By 200 million years, these protogalaxies have already gone through several generations of star formation, creating the massive, mature galaxies Webb observes at high redshift. This scenario is speculative, but it's the kind of thinking that pre-Big Bang cosmologies enable. They provide a framework where the initial conditions can be different without breaking all the other observations that constrain cosmology. The cosmic microwave background, for example, tells us about conditions at 380,000 years after the Big Bang, but it doesn't directly constrain what happened in the first moments. If the very early universe had more structure than we've assumed, but that structure was smoothed out or evolved by 380,000 years to match what we observe in the CMB, then the CMB constraints would still be satisfied. The key is finding a mechanism that creates early structure without creating too much structure, threading the needle between solving the James Webb problem and maintaining consistency with everything else we've measured. Now, let me introduce you to another radical idea that some cosmologists are beginning to take seriously: the possibility that the fundamental constants of nature were different in the early universe. We assume that things like the strength of gravity, the speed of light, the mass of the electron, and so on are constant across time and space. But what if they're not? What if these constants are actually fields that can vary, and in the early universe, they had different values than they do today? This idea isn't as crazy as it sounds. In many theories of physics beyond the standard model, including string theory, what we call constants are actually the values of scalar fields that have settled into their current state. These fields could have had different values in the early universe before they relaxed to their present values. If fundamental constants were different in the early universe, the physics of star formation and galaxy formation could have been completely different. For example, if gravity were stronger in the early universe, structures would collapse faster and form earlier. If the fine structure constant, which determines the strength of electromagnetic interactions, were different, nuclear fusion rates would change, affecting how stars burn and evolve. If the mass of the electron were different, the chemistry of the universe would be different, affecting how gas cools and contracts. Any of these changes could potentially accelerate structure formation, allowing galaxies to form earlier and grow faster than standard physics predicts. The cosmologist Joel Maguayo and his collaborator John Barrow have developed theories of varying speed of light cosmology, where the speed of light was much higher in the early universe than it is today. This would solve some of the same problems that inflation solves, like the horizon problem, but through a different mechanism. If light traveled faster in the early universe, distant regions could have been in causal contact even without inflation, explaining why they have the same temperature. More relevant to our discussion, if the speed of light was higher, or if other constants were different, the timescales for astrophysical processes could be compressed. Events that take hundreds of millions of years today might have taken only tens of millions of years in the early universe. These varying constants theories are controversial because they're hard to test, and because they seem to open the door to explaining anything by adjusting the constants ad hoc. But they're not completely unconstrained. The constants can't vary arbitrarily because they have to reproduce all the observations we've made of the universe at different epochs. The cosmic microwave background, the abundance of light elements from Big Bang nucleosynthesis, the observed expansion history, all of these constrain how much variation is allowed. Still, within those constraints, there might be room for enough variation to affect early structure formation significantly. Here's another twist. Some physicists have proposed that what we call the Big Bang might actually have been a big bounce, a moment when a contracting universe reached a minimum size and then began expanding again. In loop quantum gravity, one of the leading approaches to quantum gravity. The extreme densities and temperatures that classical general relativity predicts at the Big Bang are avoided. Instead, quantum effects create a repulsive force that prevents the universe from collapsing to a singularity. The universe contracts to a minimum size, then bounces and begins expanding. From our perspective, living in the expanding phase, this bounce looks like a Big Bang, but it's not a creation event. It's a transition from contraction to expansion. In a bouncing cosmology, the universe could be infinitely old, going through endless cycles of contraction and expansion. Or there might have been just one bounce, with the universe existing in a contracting phase for some finite time before bouncing into the current expanding phase. Either way, the bounce model allows for the universe to have a history before the apparent Big Bang. And that history matters. During the contracting phase, structures could have formed through gravitational instability, just like they do in the expanding phase. As the universe contracted, these structures would have been compressed and heated. At the moment of the bounce, when the universe reached maximum density, these structures might have been partially destroyed, but not entirely. Information about their distribution, or seeds from their remnants, could have survived the bounce and influenced structure formation in the expanding phase. Aurelian Barrau and his colleagues at the University of Grenoble have done detailed calculations of what would survive a bounce. They find that while most structure would be erased, certain patterns, particularly in the distribution of primordial black holes if they existed, could survive. These surviving seeds could dramatically accelerate galaxy formation in the post-bounce expanding phase, potentially explaining the James Webb observations. The bouncing universe model also makes specific predictions about the cosmic microwave background that differ slightly from standard inflation, predictions that future observations might be able to test. Let me pull back for a moment and give you the big picture of where we are in this investigation. We started with the shocking James Webb observations. Massive, mature galaxies at times when they shouldn't exist. We explored the standard Big Bang timeline and saw that these observations don't fit. We then examined pre-Big Bang cosmologies, eternal inflation, ekpyrotic collisions, conformal cyclic cosmology, bouncing universes that provide frameworks where the Big Bang is not an absolute beginning. These frameworks open up new possibilities for explaining the observations. Enhanced initial conditions from prior states, primordial black holes from pre-Big Bang eras, varying constants that compress timescales, or surviving structures from contracting phases. We've also looked at more conservative explanations: super-efficient star formation, primordial black holes as seeds, feedback from early supermassive black holes, and the possibility that the first stars were more effective at building galaxies than we thought. The truth is probably some combination of these factors. The universe is complex, and rarely does a single mechanism explain everything. But what's becoming clear is that our standard model of cosmology, lambda c dm, is being stress-tested in a way it hasn't been before, and it's showing cracks. The question now is, which explanation is correct? Or more accurately, which combination of explanations is correct? How do we distinguish between these possibilities? This is where the next decade of observations becomes crucial. The James Webb Space Telescope is continuing to observe. Every few months, new deep field observations are released, finding more high redshift galaxies, refining our understanding of their properties. But Webb isn't alone. There are other telescopes and instruments coming online that will provide complementary information. The Atacama Large Millimeter Array, ALMA, observes in millimeter and submillimeter wavelengths, which are sensitive to coal dust and molecular gas. ALMA can detect the raw materials for star formation in distant galaxies, telling us how much fuel these galaxies have and how efficiently they're converting it into stars. If the massive early galaxies Webb finds are exceptionally efficient at forming stars, ALMA should see evidence of that in their gas content and star formation rates. Observations are ongoing, and preliminary results suggest that some of these early galaxies do indeed have star formation rates far exceeding what's typical for galaxies today. The European Space Agency is planning to launch the Euclid Space Telescope, which began operations in 2023, and NASA's Nancy Grace Roman Space Telescope, planned for the mid-2020s. Both will conduct wide-field surveys of the universe, observing millions of galaxies. By mapping the distribution of galaxies across cosmic time, they'll provide statistical constraints on how common massive early galaxies are and how they're distributed. If massive early galaxies are rare anomalies in special environments, their distribution will be clustered and irregular. If they're a common feature of the early universe, they'll be more uniformly distributed. This will help distinguish between explanations that require special conditions and explanations that require systematic changes to cosmology. Ground-based telescopes are also getting more powerful. The Extremely Large Telescope, or ELT, being built in Chile, will have a mirror 39 meters in diameter, dwarfing any current ground-based telescope. It will be able to take spectra of high redshift galaxies in exquisite detail, measuring not just their distances, but their chemical compositions, their stellar populations, their dynamics. This will tell us whether these galaxies really do contain old stars, whether they're chemically enriched beyond what should be possible, whether they're rotating like mature spiral galaxies or churning chaotically like young protogalaxies. These details will constrain the formation mechanisms. And then there's gravitational wave astronomy. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave detector that will be sensitive to low-frequency gravitational waves from massive black hole mergers. If supermassive black holes formed early in cosmic history and grew through mergers, LISA should detect the gravitational waves from those mergers. The rate and properties of these mergers will tell us about the population of black holes in the early universe, testing whether primordial black holes or massive first-star black holes were common enough to serve as seeds for the supermassive black holes and galaxies Webb is observing. The point is that we're entering a golden age of observational cosmology. We're not just speculating based on a few puzzling observations. We're building a comprehensive, multi-wavelength, multi-messenger picture of the early universe. Over the next 10 to 20 years, the data will accumulate, the constraints will tighten, and the competing explanations will be winnowed down. Some ideas will be ruled out, others will gain support. New ideas we haven't thought of yet will emerge. This is how science progresses, through the interplay of observation, theory, and testing. But I want to address something that might be frustrating you. You might be thinking, okay, but what's the answer? What's actually going on? Are these galaxies really older than the Big Bang or not? And the honest answer is, we don't know yet. We're in the middle of the scientific process. The observations are solid, but the interpretation is still uncertain. Different scientists favor different explanations, and all of them are smart, careful people looking at the same data. This ambiguity is uncomfortable, especially in an age where we're used to getting definitive answers instantly through a Google search. But cutting-edge science doesn't work that way. Discovery is messy, uncertain, and slow. What I can tell you is this: regardless of which explanation turns out to be correct, the James Webb observations have revealed that the early universe was far more active, more structured, and more complex than we expected. The epoch between 100 and 500 million years after the Big Bang was not the dark, quiet, simple era we thought it was. It was a time of vigorous galaxy formation, of massive stars, of growing black holes, of reionization, of chemical enrichment. The universe grew up fast, faster than our models predicted. And whether that's because the models are missing some astrophysical processes, or because the initial conditions were different due to pre-Big Bang physics, or because fundamental constants varied, or some combination of all of these, we are learning that the cosmos is full of surprises. And honestly, isn't that what makes this exciting? If science just confirmed what we already believed, it would be boring. The James Webb Space Telescope is doing what the best scientific instruments do. It's showing us things we didn't expect, challenging our assumptions, forcing us to think harder and deeper. It's revealing that nature is more creative, more complex, more fascinating than even our best theories suggested. And that's something to celebrate, even if it means admitting we don't have all the answers yet. Before we go further, I want to check in with you. We're now over 2 hours into this journey, and I know this is a lot of complex information. If you're still here, if you're still engaged, that says something about you. It says you're someone who cares about understanding reality at its deepest level. You're not satisfied with superficial explanations. You want to know how things really work, even when the answers are uncertain and complicated. That's a rare quality, and it's what drives science forward. So thank you for being here, for thinking along with me, for grappling with these ideas. Drop a comment telling me how you're feeling right now. Are you energized? Overwhelmed? Existentially terrified? I genuinely want to know. Now, let's shift our focus to something even more profound. We've been talking about observations, theories, mechanisms, all the scientific details. But I want to spend the next portion of our time together exploring what all of this means for you personally, for your understanding of your place in the universe, for how you think about time, existence, and meaning. Because ultimately, cosmology isn't just about galaxies and equations. It's about us, about human beings trying to understand where we came from and where we're going. The James Webb observations are challenging the scientific picture of cosmic history, but they're also challenging something deeper, our intuitive sense of how stories work, how beginnings and endings structure meaning, how we find our place in the grand narrative of existence. Think about how stories are structured. Every story you've ever heard, every movie you've watched, every novel you've read has a beginning, a middle, and an end. The beginning establishes the setting and introduces the characters. The middle develops conflict and explores consequences. The end resolves the conflict and provides closure. This three-act structure is so fundamental to human storytelling that it seems universal, embedded in how our minds make sense of events. And we've unconsciously applied this structure to the universe itself. The Big Bang is the beginning, the first sentence of the cosmic story. The evolution of stars and galaxies is the middle, the unfolding plot. The eventual heat-death of the universe is the end, the final chapter. It's a story with a clear arc, a narrative we can follow. But what if that's wrong? What if the universe isn't a story with a beginning, middle, and end? What if it's more like an ongoing serial, a soap opera that's been running forever and will never conclude? Or what if it's an anthology series, with each episode, each eon or cycle, being a self-contained story, but the series itself having no beginning or end? These alternative structures are harder for us to grasp emotionally because they don't match the narrative patterns we're used to. Stories without beginnings feel incomplete. Stories without endings feel unresolved. But the universe doesn't owe us a narrative structure that makes emotional sense. It just is what it is. The idea that the Big Bang might not be the ultimate beginning is psychologically challenging because it removes a clear origin point. Humans like origins. We like creation myths. Every culture throughout history has had stories about how the world began, whether it's God speaking creation into existence, or cosmic eggs hatching, or giants being slain to create the earth and sky. These stories provide a sense of foundational meaning. They answer the question, where did we come from? With a definitive moment of creation. The Big Bang Theory, for all its scientific sophistication, functions psychologically like a creation myth. It gives us a moment of beginning, a point where the cosmic story starts. If that beginning is revealed to be just a transition point, if there was something before and something before that, stretching back infinitely or through countless cycles, then the question, where did we come from, loses its simple answer. We came from the previous state, which came from the state before that, which came from the state before that, in an infinite regress. There's no ultimate origin, no foundational moment, no bedrock of certainty. For some people, this is liberating. It removes the need to explain the ultimate beginning, because there is no ultimate beginning to explain. For others, it's deeply unsettling. It means we're floating in an endless chain of causation, with no anchor, no starting point, no ultimate reason for why things are the way they are. Let me connect this to your personal life. Think about your own existence. You exist because your parents existed. Your parents exist because their parents existed, and so on back through countless generations. If you trace your lineage back far enough, you reach the first humans, then earlier hominids, then earlier mammals, then the first life on Earth, then the formation of Earth, then the formation of the Sun, then the gas clouds that collapsed to form the Sun, then the Big Bang. In the standard cosmology, the chain of causation stops there. The Big Bang is the ultimate origin, the beginning of everything, including you. You exist because the Big Bang happened 13.8 billion years ago. But if the Big Bang wasn't the beginning, if there were prior states or cycles, then your causal chain extends further back. You exist because of the Big Bang, which happened because of a brain collision, which happened because brains existed in a higher dimensional space, which existed because of some deeper structure, which existed because, and the chain keeps going. Does that change anything about your existence? In a practical sense, no. You're still here, living your life, regardless of what happened in the pre-Big Bang multiverse. But in a philosophical sense, it might change how you think about meaning and purpose. If the universe has a beginning, there's at least the possibility that the beginning was designed or intended, that there's a reason for existence, a purpose built into the structure of reality from the start. If the universe is eternal or cyclic, with no ultimate beginning, then the question of purpose becomes more ambiguous. There's no starting point where purpose could have been injected. Things just are, proceeding according to the laws of physics, with no deeper teleology. This is closer to the Buddhist concept of dependent origination, the idea that everything arises from causes and conditions with no first cause, no creator, no ultimate ground of being. I'm not trying to push you toward any particular philosophical or religious conclusion. Different people will react to these cosmological possibilities in different ways, depending on their existing beliefs and temperaments. My point is simply that the James Webb observations, by challenging the Big Bang's status as an absolute beginning, also challenge the psychological and philosophical frameworks we've built around that beginning. We're being forced to think more carefully about what beginning means, about whether existence requires an ultimate origin, about how we find meaning in a cosmos that might be far stranger and more open-ended than we imagined. Let's explore another angle. One of the most profound aspects of modern cosmology is the realization that we are made of stardust. Every atom in your body, except for hydrogen, was forged inside a star or in a supernova explosion. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was created by nuclear fusion in the hearts of stars that lived and died before the sun formed. You are literally composed of the remnants of dead stars. This is a beautiful and humbling realization. It connects you directly to the cosmos. You're not separate from the universe, observing it from the outside. You're part of it, made of it, a temporary arrangement of cosmic matter that happens to be conscious and asking questions. Now add the possibility of pre-Big Bang cosmology or cyclic universes. If the universe goes through cycles, then the atoms in your body might have been through previous cycles as well. That carbon atom in your DNA might have been part of a star in a previous eon, billions of cycles ago. It's been recycled through cosmic birth and death countless times. You're not just stardust. You're multi-eon stardust, matter that has persisted through transformations we can barely imagine. Or if the universe emerged from eternal inflation, then your atoms might have originated in the inflating multiverse, perhaps even in a different bubble universe, before somehow making their way to our bubble. The causal chain connecting you to the cosmos extends further and becomes even more complex. Does this change the significance of your existence? Again, that's for you to decide. Some people find comfort in continuity, in the idea that matter and energy are never truly created or destroyed, just transformed. Your atoms have existed in some form for an unimaginably long time, perhaps eternally, and will continue to exist in some form after you die, becoming part of other structures, other beings, other stories. There's an immortality in that, not of your individual consciousness or identity, but of the substance you're made of. Others find this impersonal and unsatisfying. What good is the immortality of atoms if my subjective experience, myself, is finite and will end? There's no correct answer to these existential questions, but I think they're worth sitting with, worth feeling the full weight of. The James Webb Space Telescope is showing us that the universe is not what we thought. And when the universe changes, we change too, because we're part of it. Our sense of self, of time, of meaning, all of these are intimately connected to our cosmological understanding. As that understanding shifts, we have to reconstruct our inner models of reality, our sense of how we fit into the grand scheme of things. Let me share something personal. When I first learned about the James Webb observations, my initial reaction was excitement. New data, mysteries to solve, the universe being weird and surprising. But as I dug deeper, as I read the papers and thought about the implications, a different emotion crept in. It was something like vertigo, a feeling of the ground shifting beneath my feet. I'd spent years building a mental model of cosmic history, the Big Bang, the Dark Ages, the first stars, the gradual formation of galaxies over billions of years. I could visualize it, tell the story, feel like I understood it. And now that model was being challenged. The timeline I'd internalized might be wrong. The beginning I'd accepted might not be the beginning at all. It's disorienting to have your fundamental assumptions questioned. It's uncomfortable. Part of me wanted to dismiss the observations, to assume they'd be explained away eventually, to preserve the comfortable model I already had. But that's not how science works, and it's not how intellectual honesty works. When the evidence challenges your beliefs, you have to follow the evidence, even when it leads somewhere uncomfortable. That's the price of caring about truth. You have to be willing to be wrong, to have your worldview overturned, to rebuild your understanding from scratch. And here's what I've realized through this process. The discomfort is actually valuable. It's a sign that you're engaging with reality rather than just reinforcing your existing beliefs. It means you're growing, expanding your capacity to understand complexity and ambiguity. The universe doesn't owe us simple answers or comforting narratives. It's under no obligation to make sense in ways that feel satisfying to human psychology. Our job, as conscious beings trying to understand existence, is to stretch our minds to accommodate reality as it actually is, not as we wish it were. So if you're feeling disoriented or unsettled by what we've discussed so far, that's okay. That's appropriate. You're grappling with genuinely difficult ideas, ideas that challenge some of the most basic assumptions about existence. Sit with that discomfort. Don't rush to resolve it. Let yourself exist in the uncertainty for a while. Some of the deepest insights come not from having answers, but from learning to live with questions, from developing the capacity to tolerate ambiguity and keep thinking even when you don't have closure. Now, let's talk about something that might help anchor you amidst all this cosmological uncertainty. The fact that regardless of whether the Big Bang was the beginning or just a transition, regardless of whether the universe is 13.8 billion years old or eternal, regardless of whether galaxies formed in 100 million years or 500 million years, none of that changes the immediate reality of your existence. you're still here. The sun still rises. Trees still grow. Music still moves you. Love still matters. The scale of your daily life, the realm of human experience, is almost completely decoupled from cosmic timescales and cosmic origins. This is both humbling and empowering. It's humbling because it reminds you how small and brief your existence is compared to the cosmos. Your entire life, even all of human history, is less than a blink in cosmic time. But it's empowering because it means your life's meaning doesn't depend on solving cosmic mysteries. You don't need to know whether the universe is eternal or had a beginning to live a meaningful, purposeful, connected life. The meaning you create through your relationships, your work, your growth, your compassion, that meaning is real and valuable regardless of the cosmological framework it exists within. There's a Zen koan that captures this beautifully. Before enlightenment, chop wood, carry water. After enlightenment, chop wood, carry water. The point is that profound insight into the nature of reality doesn't fundamentally change the practical necessities of existence. You still have to live to do the work of being human. The difference is in how you understand it, the context you bring to it, the awareness you have of the larger picture. Learning that the universe might be eternal, or cyclic, or a bubble in a multiverse doesn't change what you need to do today. But it might change how you feel about doing it, the sense of wonder or perspective you bring to even mundane tasks. Let me offer you a practice, a way of relating to these cosmological ideas that might help integrate them into your life. When you look up at the night sky, when you see stars, take a moment to really comprehend what you're seeing. Those points of light are other suns, vast nuclear furnaces millions or billions of miles away. The light you're seeing left those stars years, decades, centuries, or millennia ago. You're literally looking back in time. Some of those stars might not even exist anymore. They might have exploded as supernova, but their light is still traveling toward you, a ghost of something that once was. Now add what you've learned today. Those stars are part of galaxies, and those galaxies formed over billions of years through processes we're only beginning to understand. And according to the James Webb observations, the early universe was already populated with massive galaxies when it was supposedly too young for them to exist. The cosmos has a history, a deep history that extends back to the Big Bang and possibly beyond. When you look at the night sky, you're seeing a snapshot of that history, a cross-section of cosmic time frozen in the pattern of lights above you. Feel the weight of that. Feel the temporal depth, the vast stretches of time that separate you from those distant lights. And then feel the connection, the atoms in your eyes, the neurons firing in your brain. As you process the image, those atoms were forged in stars like the ones you're looking at. You're made of the universe, observing itself, a way for the cosmos to know itself. That connection is real regardless of whether the Big Bang was the beginning or a transition. It's real regardless of whether galaxies formed in 100 million years or 500 million years. You are cosmos made conscious, and that's extraordinary. This is what I mean by integrating cosmological knowledge into your lived experience. It's not about memorizing facts or winning arguments about the age of the universe. It's about cultivating a sense of awe, of connection, of perspective that enriches how you move through the world. The James Webb observations, for all their technical complexity, ultimately point to something simple and profound. The universe is vast, old, mysterious, and full of wonders we're only beginning to discover. And you're part of it, intimately woven into its fabric. Your existence made possible by 13.8 billion years, at least, of cosmic evolution. Before we move to our final section, I want to hear from you. In the comments, tell me, has your sense of your place in the universe changed as you've listened to this? Do you feel smaller or larger, more connected or more isolated, more certain or more uncertain? There are no wrong answers. I'm genuinely curious how these ideas are landing for different people. how the same information can create such different emotional and philosophical responses depending on who's receiving it. We're approaching the end of our journey together, but I have one more crucial topic to cover. What happens next? Where do we go from here, both as a scientific community and as individuals trying to make sense of existence in light of these revelations? What are the next questions to ask? What are the implications if various explanations turn out to be correct? And how do you, personally, integrate this knowledge into your ongoing life? That's what we're exploring in this final stretch, so stay with me. We're bringing this all together in a way that will leave you with not just information, but with a new lens through which to see reality itself. Let's start with the scientific next steps. Over the next 5 to 10 years, as more data comes in from James Webb and other telescopes, certain scenarios will gain support while others are ruled out. If it turns out that the massive early galaxies are explained by conventional astrophysics, just with higher efficiency star formation and contributions from early black holes, then the Big Bang timeline stands. The universe is 13.8 billion years old. The Big Bang was the beginning, and we simply underestimated how quickly galaxies could form under the right conditions. This would be a relief to many cosmologists, because it would mean our fundamental framework is correct, just needs refinement. Lambda CDM survives, and the crisis passes. But even in this best-case scenario, we've learned something profound. We've learned that the early universe was more dynamic and complex than we thought. We've discovered that supermassive black holes formed earlier than we expected. We found that star formation can be far more efficient than we see in the nearby universe. We've pushed our understanding of how structure emerges from chaos, how order arises from the near-uniform primordial plasma. That's significant. It expands our knowledge of what's possible in astrophysics. Now, the more interesting possibility. What if conventional astrophysics can't explain the observations, no matter how much we tweak the parameters? What if the number of massive galaxies, their level of maturity, and their existence at extreme redshifts simply cannot be accommodated within the standard timeline? Then we're forced to consider more radical alternatives. This is where pre-Big Bang cosmologies become necessary rather than speculative. If the data demands it, cosmologists will have no choice but to seriously develop and test models of eternal inflation, ekpyrotic collisions, cyclic cosmologies, or bouncing universes. The challenge is that these models are harder to test than standard cosmology. They make predictions about the very early universe, times and energy scales we can't directly probe, but they're not completely untestable. Each model makes specific predictions about patterns in the cosmic microwave background, about the distribution and properties of galaxies at different epochs, about the nature and abundance of gravitational waves from the early universe. As our observational capabilities improve, we can check these predictions. It will take time, perhaps decades, but gradually the viable options will narrow. If eternal inflation is correct, we live in one bubble of a vast multiverse, and other bubbles exist beyond our cosmic horizon. We'll never be able to observe those other bubbles directly, unless we happen to collide with one, which would be a catastrophic but unmistakable event. But we might find indirect evidence, anomalies in the cosmic microwave background, unexpected correlations in the distribution of galaxies, signatures that our bubble isn't perfectly isolated. The search for these signatures is ongoing. If the ekpyrotic or cyclic models are correct, then the universe is much older than 13.8 billion years, though that number still represents the time since the most recent bounce or collision. The total age might be infinite, or it might be finite, but vastly longer than we've assumed. In these scenarios, information from previous cycles might be encoded in the structure of spacetime or in the distribution of matter. Finding and decoding that information would be one of the greatest achievements in the history of science, like discovering a message from a previous version of the universe. If Penrose's conformal cyclic cosmology is correct, then the universe literally has no end, Or rather, its end is the beginning of the next eon. The implications are dizzying. It means existence is truly eternal, with no ultimate beginning or end. The universe is a self-perpetuating cycle, each eon setting up the conditions for the next. In this model, the question, why is there something rather than nothing, is answered with because nothing is unstable and existence is the natural state. Whether that's a satisfying answer is up to you. Each of these scenarios implies a different relationship between ourselves and the cosmos. In the multiverse scenario, we're incredibly special, not because we're at the center or because we're unique, but because we're the outcome of an anthropic selection process across infinite possibilities. Out of 10 to the 500 power possible universes, we exist in one of the tiny fraction that can support complexity and life. That makes our existence improbable in a sense, but also necessary. We must find ourselves in a universe like this because we couldn't exist anywhere else. In the cyclic scenario, we're temporary, but what we're made of is eternal. The matter and energy in our bodies has been through countless cycles and will go through countless more. There's a continuity to existence that transcends individual lives or even individual eons. This can be comforting or unsettling, depending on whether you value continuity of substance over continuity of identity. In all of these scenarios, the key insight is that the Big Bang, that moment we've treated as the beginning of everything, might just be a chapter in a much longer story. And that realization, more than any specific theory, is what's truly revolutionary. It's a paradigm shift comparable to when humans realized Earth wasn't the center of the universe, or when we realized our galaxy was one of billions. Each time, our sense of cosmic significance shrinks in some ways and expands in others. We're less central, less special in our physical location or timing, but we're more connected, more deeply embedded in a cosmos that's vaster and stranger than we imagined.